Thank you. It's great to be here. I am a chemistry professor. You might think it's a little odd, a chemistry professor talking about lasers, but all of the research that I do in my lab here at the University of Iowa uses lasers to look at how molecules move and interact as they do chemistry. So the things I'm going to tell you about today, I want to tell you a little bit about how lasers work, because that'll be really important for understanding some of the laser science that they're going to talk about in the movie. So does anybody know what the acronym LASER stands for? LASER, the word, is actually an acronym. No? It stands for Light Amplification by Stimulated Emission of Radiation. That's complicated, right? So let's break it down. Light amplification is exactly what it sounds like. It's going to amplify light. We're going to take a little bit of light, we're going to make it into a lot of light. So light amplification, that's what a laser does. And it does it by a process known as stimulated emission. And so to tell you about stimulated emission, I first have to back up and tell you just a little bit of chemistry. Just a little bit, I promise, it's just a little bit. So atoms and molecules have electrons in them. All of the electrons in atoms or molecules occupy what are known as energy levels, right? So this is a little bit like climbing a ladder. You can stand on the rungs of a ladder, and you can be on the ground. That's the ground state, the lowest energy level, or you can climb up the ladder, and every rung is a higher energy level. And of course, the higher you go on the ladder, the less stable you are. That's true for electrons and atoms and molecules as well. And so most of the time, the electrons and atoms and molecules like to stay in the lowest energy level, the ground state. But you can excite them, and the way that you excite electrons is that they absorb a photon. A photon is a particle of light. So electrons in atoms or molecules absorb light. They go to a higher energy level. They step up to one of those higher rungs. And if they emit light, they can go from one of those higher energy levels. Hey, can we roll off the base at all on this? That'd be really cool. And if they emit light, so they emit a photon of light, they can go from a higher energy level to a lower energy level. So they jump from one energy level to another by either absorbing light to go up or emitting light to go down. Okay, with that background, you can understand everything about how a laser works. So the whole trick to a laser is you're going to do this process called stimulated emission. So I said if electrons are in a higher energy level, they can emit. That means they're going to dump a photon out, and they're going to drop down to a lower energy level. If you wait for that to happen spontaneously, it takes a long time. What do I mean by a long time? It might take microseconds. In my world, that's a really long time. Microseconds is forever for me. So for electrons to sit there and, they're in their excited energy level, and they wait and they wait and they wait, eventually they'll emit a photon. Or you can do this clever trick called stimulated emission. So if you shine light on an electron in the ground state, it'll absorb, if it's the right wavelength, it's the right energy, it'll absorb that light and jump up to a higher energy level. If you shine the same color of light on an electron in that excited energy level, it will stimulate it to emit light to go back to down to the ground state. Right? So stimulated emission, you shine light on it to prompt that to emit its photon, to dump that energy to go back to the ground state. And so the way a laser works is you're going to set up atoms or molecules in excited energy levels, and then you're going to get a little bit of light in there, and that will stimulate emission. They'll go back down to the ground state, making more light, right? So light amplification by stimulated emission of radiation. The radiation in this case is the light. Okay, so that's basically how a laser works. So what do you need? So you're going to need a way for light to bounce back and forth. So you need some end mirrors. You're going to have to define a cavity that allows you to trap the light to bounce back and forth. And then you're going to need a gain medium. You're going to need these atoms or molecules in excited energy levels. Now the trick is you can't just excite a few of them, right? Remember, if I shine light on the atoms or molecules and they're in their ground state, they absorb. And if they're in their excited state, they emit, and it's the same color of light that stimulates emission as also stimulates absorption. And so, if I have more molecules in the ground state or atoms in the ground state than I have in the excited state, I'll absorb more light than I emit. So to get amplification, I have to set up a situation in which all or almost all of the molecules or atoms are in the excited state, so that when I stimulate emission, I get very little absorption, and I get a net gain, a net increase, an amplification of the light. That means I've got to take the atoms and molecules and put more of them in the excited state than there are in the ground state. I told you, atoms and molecules in the excited state, that's not stable. That's called a population inversion. That's really hard to do. It turns out you got to use real tricks to convince atoms or molecules to population invert, to put more of the electrons in the excited state. So there are a couple of strategies for doing that. Actually, there are a number of strategies for doing that. I'm only going to tell you about a couple. Inside this box, there's a little glass tube. That little glass tube contains a mixture of helium and neon gases. Helium and neon are two elements. They're noble gases. We'll get back to noble gases more in a minute. And if I turn this laser on, I'm going to turn it around the other way to turn it on, because I don't mind shooting the wall over there, but I don't know what's over there. So, all right, so it lights up, and you can see there's a little red dot over there. So what's going on here is inside this tube, I said I have helium and neon, and when I turn this on, it sets up a high-powered, high-voltage discharge. This works exactly like a neon sign, right? So you see neon signs around. Those aren't lasers. They're a high-voltage discharge with a pure gas. That high-voltage discharge literally rips the electrons off of the atoms, and as the electrons and the atoms recombine, they start falling down the energy levels, emitting photons, and they shine light. Well, we're doing the same thing here. We've got a high-voltage discharge ripping the electrons off of the atoms. Those electrons, as they reattach to the atoms, start dropping down the energy levels, dropping down towards the ground state. As they do, they emit light that can initially go in all directions, but some of it will go down the axis of the tube, and you can see there's a little red glow from a mirror on this end, and if you look closely, there's a little red glow from a mirror on this end. I've got in mirrors on my tube, and so any light that spontaneously goes down the tube reflects back off the mirror, goes to the other end, and reflects back and goes to the other end, and go back and forth, and it's trapped in here, and every time it goes back and forth, it stimulates more emission. That's how you get light amplification, and it builds up enough light that actually all that comes out the end here is the leakage through the mirror. So that mirror is just a slightly leaky mirror. There's a huge amount of light inside the laser cavity, inside the mirrors, and then what gets out in this case is just a little bit. So one strategy you can use is this kind of high voltage discharge. Lots of lasers work that way. The other strategy you can use, and the one that they're going to talk about in the movie, is a funny kind of laser called an Excimer laser. Right, so I mentioned noble gases. Noble gases are these elements that are, oddly enough, gases that are completely unreactive. You can put them with any kind of reactive material you like. They just don't do anything. So these are things like helium, neon, argon, krypton, xenon. They don't react with anything. They're noble gases. It turns out that's true as long as these are in their ground electronic state. As long as all of the electrons are in the ground state, they're very stable atoms. They don't do anything. If you excite them, however, they can be very reactive. And so an Excimer laser is formed by putting a mixture of halogens, so things like chlorine, fluorine, or bromine, into a big tube, a big gas tube, along with a noble gas. Typically, the most common ones are argon, krypton, or xenon. And when you make that mixture, nothing special happens because the noble gases are unreactive. But again, if you apply a high voltage discharge, you'll excite the electrons in the noble gas and in the halogen, and then the noble gas and halogen in an electronic state, excited state, will get together, forming a stable molecule, a stable excited state molecule called an Excimer complex or an exaplex. In the excited electronic state, that turns out to be a stable molecule. In the ground electronic state, there is no such stable molecule. It completely falls apart. And so now you can see how you get a population inversion. You can have a stable molecule in the excited state. There are no such molecules in the ground state, so if it emits a photon and goes down, the molecule falls apart, so you never have a ground state molecule. The ground state doesn't exist. And so if you make the molecule in the excited state, it's all population inversion. And as a consequence, these are extraordinarily efficient lasers. They're really powerful. In fact, these were, if anybody's ever had laser eye surgery, for a long time, these were the way you got laser eye surgery. There was typically a xenon chloride laser that was widely used for laser eye surgery from the mid-90s until about the mid-2000s. And then they started to go to other laser technologies. What they're going to talk about in the movie is the idea of excited bromine in an argon matrix will form an exaplex that lasers like a stick of dynamite. It's exactly this same idea of an Excimer laser in the gas phase, except they're going to talk about making it in the solid state. We're going to make this in a frozen argon matrix. Now, the trick to going into the solid state, what limits the power you can get out of a typical Excimer laser is that it's in the gas phase. And so you have a limited number of atoms that you can get, a limited number density of atoms in the gas phase. If you do that in the solid state, you can increase the number density by about 1,000-fold. And in so doing, in principle, you ought to be able to increase the power density of the Excimer laser by something like 1,000-fold, which would be a truly enormously powerful laser to be sure. It turns out that at the time the movie was made, that was a technology that people were playing with to try and see if they could make it work. No one's ever made a solid-state Excimer laser work. People have tried a lot. In fact, the U.S. government spent a long time trying to make solid-state Excimer lasers for very much the reasons described in Real Genius, right? Since the early 1980s, when the Reagan administration launched the Star Wars program. No, that's not George Lucas. That's Ronald Reagan. Anybody heard of the Star Wars program? Yeah, oh, good. It's not all young people here. Yeah, the Star Wars program was a program that the Reagan administration started, and the premise was we were going to put lasers in satellites in outer space, and that when Russia launched their missiles at us, nuclear warheads, we would shoot them down by shooting lasers at them in outer space. This was the premise. It turns out this crazy idea funded an enormous amount of really cool laser science for about 20 years, so it wasn't all bad. And, frighteningly enough, Lockheed Martin still is working on this idea, and they actually have now laser-based weaponry that they're selling to the U.S. government. So it seems like a far-fetched idea. It's not totally crazy. What is totally crazy, as Rebecca said, however, is popping popcorn. So in the movie, they're going to show you their laser-based weapon is going to shine a beam of light down into this house, the professor's house. Professors do not live in houses that nice, by the way. Just spoiler alert. And it's supposed to pop this popcorn. Yeah, so it turns out if you try to pop popcorn with a laser, that's not going to work so well. So popcorn pops because when you heat it up, the water inside turns to steam, and that causes the kernel to explode, and the popcorn kernel pops. If you shine laser light on a popcorn kernel, you can heat up one side pretty effectively. That one side will burn before the whole thing gets hot enough to actually cause it to pop. If you rotate it carefully, fast enough, you can actually get it to heat uniformly enough so that it will, in principle, pop, as long as your laser's not too powerful. Most of them will burn it up before they actually pop it. You could never actually get a whole pile of popcorn to pop. There aren't lasers big enough to do that. All right, that tells you a little bit about lasers. I want you to watch for excited bromine in an argon matrix, because that's really cool. Are there questions I can answer about lasers before we get started? All right, let's get to the video.